Welcome back to my YouTube channel. Today we will discuss an important theorem of cyclic group theory. Okay, statement of the theorem is say that G be a group, okay, and any element A belongs to G. If A has infinite order, then A to the power I equal to A to the power J, if and only if I equal to J. And if A has finite order, say n, then generator of A equal to identity A square dot dot A to the power n minus 1, and also A to the power I equal to A to the power J if and only if n divides I minus J. Okay, now prove. First of all, suppose A has infinite order. Okay, order of A is infinite. So by the definitions of order, so there does not exist any natural number n such that A to the power n equal to identity. Okay, now A to the power I equal to A to the power J, where without loss of generality, where I greater than J. Okay, so this implies A to the power I minus J equal to identity. Okay, and here I minus J is positive integers, but here already given there does not exist any natural number such that A to the power n equal to identity. So this implies I minus J must be equal to 0. So this implies I equal to J. Okay, and conversely, if I equal to J, this implies A to the power I equal to A to the power J, and which is trivial. Okay, so first part of the theorem is done. Now second part, we will show that generator of A equal to identity A square dot dot A to the power n minus 1. Okay, where order of A equal to n, that is finite order. Okay, so suppose S equal to identity A square and dot dot A to the power n minus 1. Okay, now idea of the proof as follows. First we show that generator of A subset of S and S is also subset of generator of A, then we conclude that generator of A equal to S. Now this idea use here. Okay, so let any element x belongs to S. Okay, so this implies x equal to sum A to the power k, where k belongs to 0 1 dot 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 n minus 1. Okay, and we already know that every element of generator of A, that is form as A to the power n. Okay, for n is n belongs to Z. Okay, so this implies x belongs to generator of A. So this implies S is a subset of generator of A. Okay, so this is equation 1. Now next we show that generator of A subset of S. So let any element y belongs to generator of A. So y written as A to the power k for some k. Okay, so by division algorithm theorem, there exist integer q and r such that k equal to q n plus r. Okay, where r lies between 0 and strictly less than n. Okay, so a to the power k, this is equal to a to the power q n plus r, this is equal to a to the power n to the power q dot a to the power r. Okay, and here given order of a equal to n, that is a to the power n equal to identity. So this equal to identity to the power q dot a to the power r. So this equal to a to the power r. Okay, and r lies between 0 and strictly less than n, and also here define the set of S, all element of S form as a to the power k, where k belongs to 0 to n minus 1. Okay, so this implies a to the power r belongs to S. Okay, so we have a to the power k belongs to S, so this implies y belongs to S, where y is arbitrary element of generator of A. So therefore we have generator of A subset of S. This is my equation number 2. So from equation 1 and 2, here 1, S is subset of generator of A and 2 is generator of a subset of S. We have S equal to generator of A, that is generator of A equal to identity A square dot dot a to the power n minus 1. Okay, now first part is done. Now next we show a to the power I equal to a to the power j if and only if n divides I minus j. Okay, so now a to the power I equal to a to the power j. Okay, where I strictly greater than j. Okay, so this implies a to the power I minus j equal to identity. Okay, by again division algorithm theorems, there exist integer q and r such that I minus j equal to q n plus r, where r lies between 0 and strictly less than n. Okay, so this implies a to the power I minus j equal to a to the power q n plus r, and similarly we have a to the power r, this equal to, okay, where r lies between 0 and strictly less than n. So from this, suppose this equation number 3, from equation 3 we have a to the power r equal to identity, which is a contradiction. Why? Because order of a equal to n, that is a to the power n equal to identity, where n is the least positive integer, but here r is strictly less than n and also positive and also integers, which is a contradiction. Okay, so this implies r must be equal to 0. Okay, so suppose this is equation star. Okay, so from star we have I minus j equal to qn. Okay, so that is where q is integer belongs to z, so this implies n divide I minus j. Okay, now we show that n divide I minus j, this implies a to the power I equal to a to the power j. Okay, so now n divide I minus j. Okay, so that is I minus j equal to nk for some k belongs to z. Okay, So this implies a to the power I minus j, this equal to a to the power n k, and that is a to the power n to the power k, but order of a equal to n. So this implies a to the power n equal to identity. So this implies identity to the power k, this equal to identity. So we have a to the power I minus j equal to identity. So this equal to a to the power I equal to a to the power j, and hence the proof.